This presentation is for CM4563, Group 1, consisting of Charles Mitchell, Mary Tenkate, Kirkland Dewberry, and Juan Nunez. Today we will discuss a new type of material that has far-reaching implications in the landscapes of construction and engineering, cellular concrete. As technology has improved, our use of an ancient material has as well. Cellular concrete challenges norms and offers many advantages over other conventional construction materials. This material is lightweight and strong for its weight. It offers many advantages over traditional concrete and can be more efficient and sustainable. We will look at composition, testing standards, and applications of this wonder material as well as future implications. Cellular concrete comes in various types, tailored for diverse applications. Aerated concrete, created by introducing air bubbles into a cementitious mixture, offers excellent insulation properties and is ideal for walls. Foam concrete, made by blending a cementitious slurry with preformed foam, exhibits low density and is suitable for filling voids. Autoclaved aerated concrete undergoes a controlled curing process, enhancing its strength for structural prefab elements. Polymer-based cellular concrete incorporates polymers for added durability and is often used in overlays and repairs. Each type of cellular concrete provides unique benefits, addressing specific project requirements.
ACI 523 defines low-density cellular concrete as a hardened material with an oven-dry density of 50 pounds per cubic foot or less, made of hydraulic cement, water, or preformed foam. Let's take a closer look at these materials. We start with a cement. It can either be a Portland cement in adherence to ASTM C150, type 1, 1, 2, or 3. It can be a 595 cement, which is also called blended cements, or it can even be a ASTM C1157 performance cement. Then we have water, clean and potable. You mix it with the cement and you mix it with the foaming agent, so you want to make sure there's no contamination in your water. And then we have the air, which is used to create the foam. Contaminants in your air or in your air compressor, like oils, can cause unstable foam and or density issues. So what is preformed foam? It is governed by ASTM C869, that's the specification, and then there's testing methods on how to actually test the foam for adherence to C796. They're proprietary formulations, so we don't know exactly what makes them, but they're usually hydrolyzed proteins or synthetic surfactants. The density on it's usually 2.5 to 4 pounds per cubic foot. The biggest thing here is make sure you do trial batches. Those are imperative to get the foam content correct to ensure your plastic and your hardened properties. So this is an example of a typical mixing sequence. You bring the cement water slurry in with a ready mix truck. You have your foam concentrate, you have your foam generator, and you have your air compressor. Water and the air go, and the foam concentrate go into the foam generator. The slurry mix goes through a concrete pump, and then there's an inline mixer that jets it all together, and then out the end of the pump is your cellular concrete. And then on the right-hand side, there is a picture of pumping. As you can see, it's very loose, it's very fluid. It's kind of fun to watch get pumped. So what are some of the performance testing requirements? What are the specifications for cellular concrete? The requirements per your ASTM standards are density, compressive strength, tensile splitting strength, and water absorption. Of course, you're going to have some engineering specs that call for other tests. The most common ones are permeability, modulus of rupture, flowability, viscosity. So one thing to note is your quality control is actually done on your job site, not your batch plant, since you're sending a truck of slurry to the job site, not the actual finished product. You want to job site test your slurry density, your cast density, and your foam content. Your densities will tell you your foam content. And then your compressive strength. This picture is actually a proprietary product made by Elastozel for making compressive strength cylinders. Since they're so fragile, this is basically just made of styrofoam, and you use a knife to just slice it open. so you can get your cylinders out without having to strip a plastic mold. Matters. The volume of your air in your finished product will drive your density and your compressive strength. And both of those in turn drive your insulation values, your bearing capacity, your permeability values. So everything comes back to the density of the concrete. Your foam content and your water to cement and your slurry are your driving factors behind the density. So how to test slurry density? It is governed by ASTM D4380. And you want to measure it regularly to just make sure that you're getting the final product density that you're looking for. It's an easy test, it's quick, and it's easier to adjust the water to cement ratio on the front end rather than waiting until the foam is in the product and then trying to make adjustments after everything's already added. Your slurry density is typically 105 to 115. The image here is what they call a mud balance. Basically, you fill the cup on the left-hand side with your slurry. On the right side, you have a rider on an arm. It's kind of like going to the doctor's office way back in the day. You get on the scale and they have the little rider arm. And that's how they tell your weight. So density, again, field density is also called as cast. It's your ultimate QC test. This is the end all be all. If your density is not in spec, then you're going to have problems. You take samples throughout the project, whatever the engineers call for. It's usually every 30 minutes. It's a half a cubic foot measure, kind of like an air pop, but larger. You just fill it up, all tapping it with a hammer and getting all of those air voids out. You strike it off and you weigh it. And at the bottom is the formula for your final density. The weight of your full measure minus your empty divided by the volume of the measure. Now your dry density, it's 2 companion cylinders that you make at the same time as your compressive strength cylinders. You cure them exactly the same, and then you put them in an oven at 28 days. You weigh them every 24 hours until the weight doesn't change by more than 1%. Compressive strength. With cellular concrete, compressive strength is not necessarily the big driving factor. It is not necessarily structural in nature. It's just part of the entire system. So you're going to have very low compressive strength with cellular concrete. 3x6 cylinders, which is much smaller than the typical used in concrete. 4 cylinders per testing age. Typical testing age is 28 days. Don't rod the cylinders. You fill them up 2 layers. You tap them with your hand. Strike them off and cover them. Make sure they don't get any evaporation, any kind of environmental contamination. And then make sure you remove all the molds within 7 days very carefully. These cylinders can fall apart with such low compressive strengths. And then make sure you cure them properly, which we will talk about on the next page. And check your brake machine. This is very important. Most concrete brake machines are not sensitive enough for such low loads. So you definitely need to make sure you're using a brake machine that is adequate for such a small amount. So curing, initial curing, very similar to typical standard conventional concrete. Cover it, avoid areas with vibration, don't disturb them. Make sure you pack them nicely and care as exercise when you transport them back to the lab or wherever they are. Lab curing is going to be very similar. You want them in a high humidity environment. Avoid moving water, any kind of fast moving air. And then you moist cure them for 25 days. You pull them out and then you air dry them for 3 days prior to testing. Do not oven dry them. And then once they're dry for 3 days, you can use unbonded or bonded caps, and then you break them like you would concrete. And here is a nice little table that shows you how density directly affects compressive strength and bearing capacity. So typically on cellular concrete, you're looking at the 24 to 30 pound per cubic foot range. So your compressive strengths are really way down there. But this gives you a better idea of how your density directly affects your compressive strength.
Implications. This section focuses on the question, What are the implications of the low density of cellular concrete? To answer this question, we must focus on three main points: the applications in lightweight construction, the impact of transportation and installation, and the energy efficiency and sustainability implications. Let's start with the applications of lightweight construction. As we know, cellular and foam concrete are two names commonly used interchangeably when referring to lightweight construction. Some studies call it LCC, which is short for lightweight cellular concrete. Cellular or foam concrete comprises of lightweight components such as cement, water, and a foaming agent, and in some cases, lightweight aggregates. The foaming agent traps bubbles or voids in the concrete, giving it lightweight properties. To dive a little deeper into this, cellular concrete is produced by locking air voids in the mortar with the help of a suitable foaming agent which reduces density and weight. Cellular concrete is known for its versatility. This is because the application and desired strength of concrete can change due to the specific mix design and proportions of materials. This brings us back to the initial main point of the applications of lightweight construction. The use of cellular concrete has become widespread. It can be used in a wide range of applications in civil engineering because of its distinct properties, including reduced density, good flowability, self-compacting behavior, low thermal conductivity, and economic advantages. Foam concrete or cellular concrete can also be used in manufacture prefabricated wall panels and beams, corrugated panels, pavement subbase, trench filling, soil compaction, and geotechnical engineering. Cellular concrete is widely used in regions facing problems with shortages of houses, adverse weather conditions, hurricanes, and earthquakes. Some countries where cellular concrete is deployed include Turkey, Germany, England, Thailand, and the Philippines, although this form of concrete is starting to be commonly used around the world. Moving on to the second main point of this section, we will discuss the impact of transportation and installation of cellular concrete. One of the main advantages of using cellular concrete is that transportation is much more feasible when compared to conventional concrete. This is because cellular concrete is composed of lightweight ingredients and its self-weight is much less. The weight reduction is up to 80% compared to that of conventional concrete. One of the reasons cellular concrete weighs less is that cellular concrete replaces coarse aggregates with air, resulting in a lightweight foam. This foam has the stability to be calculated as a solid, but the properties to be placed as a low-density material. Another impact of cellular concrete is the ease of installation. There are many on-site installation equipment that allows the users to transport and install this concrete. Some large volume projects use high production self-contained units for quick and easy access to cellular concrete. Other on-site installation equipment includes mobile mixing units and self-contained trailers with a wet batch system. Cellular concrete eliminates coarse aggregate haul, and most job sites are cleaner and less congested due to fewer equipment and fewer truckloads. The last section for implications of low-density cellular concrete includes the energy efficiency and sustainability implications. Production of cellular concrete is more environmentally friendly than that of alternative methods. A recent study shows that cellular concrete takes up to 55% less trucking and 55% less fuel and carbon emissions. The insulating properties of cellular concrete also contribute to the energy efficiency of buildings, which reduces the need for excessive heating and cooling, which reduces energy consumption. Lastly, cellular concrete can be produced from recycled material, which is a more sustainable option. In conclusion to this question, cellular concrete is a win-win for both construction and sustainability. Cellular concrete offers a greener alternative and promotes energy efficiency.
As we've covered, the best use of cellular concrete is not for load-bearing applications. It has unique properties that make it suitable for non-structural uses and reduces the use of traditional concrete in projects where the heavy structural qualities are not needed. Strength can be designed to meet the standards needed for the project. Here we can see the options that may be available. The lightweight product is uniquely suited for many different applications.
Because of its lightweight and potentially lower density design, cellular concrete can have several limitations and negatives when compared to other conventional concrete methods. We'll go over a few of these limitations and negatives pertaining to concrete strength, material cost, setup time, and availability. One of the largest negatives to cellular concrete that could potentially limit its use in certain applications is its reduced strength compared to other, more robust conventional concrete methods. Although cellular concrete is an excellent choice for a wide range of applications, such as numerous soil stabilization and cavity and void filling applications, its compressive strength is far less than standard concrete, making it unsuitable for certain usage where higher compressive strength would be needed, such as heavy equipment foundations or retaining walls. As previously mentioned, the use of cellular concrete can potentially be a reduction in project cost. While the use of cellular concrete can have reduced transportation, handling, and even installation costs, some of the materials and equipment required can drive the cost higher than the use of typical concrete. This is especially true when producing small batches of cellular concrete. When producing large batches of cellular concrete, you have the opportunity to reduce the equipment cost per yard of concrete. In a small batch, the equipment cost could very well outweigh the cost of concrete itself. This is a very important decision that will need to be seriously considered before using cellular concrete in place of other conventional concrete applications. Although having cellular concrete trucked in from an off-site batch plant should not increase installation time, having an on-site or mobile setup on a project might. The equipment needed and materials used to batch cellular concrete may take an additional time to set up when compared to other concrete methods. If you have multiple pours lined up in several different locations across a fairly large job site, the setup time of equipment needed to facilitate these pours could very well cause significant delays due to the time needed to break down and set the equipment back up elsewhere. This is an important factor to consider when planning and estimating out your installation and execution, as you may not have the logistics to have concrete trucked in or the ability to pump from a distance, causing the need to have multiple mobilization of equipment and materials. Just as with conventional concrete and other concrete methods, the geographic area a project is in may limit the availability of cellular concrete. This is something that not only needs to be considered in the procurement and execution phases of a project, but also in the engineering phase. If you are in an area where cellular concrete is not in ready supply, or where vendors may not have the equipment you need, then cellular concrete may not be the ideal selection or solution for your application. Project location, in reference to availability, may not only limit the use of this method, but can potentially increase transport costs, increase lead time, and cause significant delays. Having to bring in equipment and material to set up a batch area on a project site from several hours away may be a viable option to reduce this limitation. However, if the supplier you are using runs into any supply chain issues, it can be a severe detriment to your project.
In conclusion, we've navigated the intricacies of cellular concrete, unraveling its nature and delving into the essential performance requirements and evaluation tests. The significance of its low-density profile has been explored, unlocking the implications for efficiency and sustainability in construction. As we compare the structural performance with conventional concrete, cellular concrete emerges as a formidable contender, showcasing its unique prowess in various applications. However, acknowledging the full picture We've also examined the limitations and negatives associated with its use in structural applications. This holistic understanding equips us to make informed decisions, leveraging the strengths while being mindful of the challenges as we pave the way for a resilient and innovative future in construction.